In this video, I will be discussing about counting techniques. Many problems in the real-life situations can be solved by simply counting the number of different ways that a certain event occur. In this video, we will learn different methods and formulas teaching us how to count without really counting. These methods and techniques result in a theory of counting called the combinatorial analysis. Combinatorial mathematics is a branch of mathematics which deals with counting principles. For example, the fundamental principle of counting provides a rule in determining the number of ways of the chance occurrence of events. So, what is fundamental principle of counting? The principle states that if one thing can occur in m ways, and each of the m ways can occur in n ways, and each of the n ways can occur in r ways, and so on and so forth, then the sequence of all things can occur in m times n times r times and so on and so forth ways. So, applying this formula to an example, let us consider example number 1 here. How many 3-digit numbers can be formed from the numbers 5, 7, and 4? Letter A, when repetition of digit is allowed. Letter B, when repetition of digit is not allowed. So, to solve this problem, there are two methods that I'm going to use here. The first method is using the listing method, and the second one is using the fundamental principle of counting, which popularly known as the box method. Now, in the listing method, we will use a device that could help us list down all possible occurrences, and this device is called a tree diagram. So first, let us draw 3 boxes here, since in the problem, we are looking for a 3-digit number that can be formed from the numbers 5, 7, and 4. So that's why in the first box, this is a box for the hundreds place, and the second box is for the tens place, and lastly, the last box is for the ones place here. So in the hundreds place, for a 3-digit numbers, we can place any of the digits there. It could be 5, 7, or 4 here. And because repetition is allowed for letter A, we can place 5, 7, or 4 in the tens place. And of course, in the ones place, you can place 5, 7, or 4 because in this case, repetition is allowed. So you can trace that we can form our first 3-digit number, which is 555. Or you can form 557, or 554, or 575, or 577, or maybe 574, or 545 here, 547, or 544. So we have list down all possible 3-digit numbers here that has 5 in the hundreds place. But we can also place 7 in the hundreds place and then trace a number which is 755, or you can have 757, or 754, or 775, or maybe 777, 774, or 745, 747, or 744. So here we have 9 more 3-digit numbers. The 3-digit numbers that starts with 7 in the hundreds place. But you can place also 4 in the hundreds place. So we can have 455 or 457, 454 or 475, 477, 474, or you may have 445, 447, and 444. So here, an additional set of 3-digit numbers which has 4 in the hundreds place. Now, if you count how many 3-digit numbers we can form out from these numbers, 5, 7, or 4, we listed down that there are 27 3-digit numbers. So, our answer here is 27 3-digit numbers when repetition of digit is allowed. So let's proceed to letter B question here. What if repetition of digit is not allowed? So how many 3-digit numbers can be formed out from these numbers 5, 7, and 4? So here, again, I'll be constructing 3 boxes. One for the hundreds digit, second for the tens digit, and the last box for the ones place. Now in the hundreds place, I can place any of the digits there. We can place 5, 7, or 4 here. But in the tens place, I cannot anymore place 5 in the tens place because repetition of digit is not allowed. So I can place only 7 or 4 here. But in the ones place, if I have used the 2 numbers in the hundreds place and in the tens place, then I have only one choice in the ones place because there are only 3 numbers that we can choose from. So if 5 is being placed in the hundreds place and 7 in the tens place, so I can have only one choice, which is 4 in the ones place. So the number is 574. But if I have placed 5 in the hundreds place with 4 in the tens place, I have only one choice remaining for the ones place, which is 7 here. So the number is 547. But if I place 7 in the hundreds place and 5 in the tens place, I have only one choice from the 3 numbers given in the problem, which is the number 4. So the number is 754. Or I can have 7 in the hundreds place and 4 in the tens place. So I have only one choice of 5 in the ones place. So the 3-digit number is 745. Or I can have 4 in the hundreds place, 5 in the tens place. So I have only one choice in the ones place, which is in this case 7 here. So the number formed is 457. And if I have 4 in the hundreds place and 7 in the tens place, I have only one choice in the ones place, which is 5. So the number is 475. So if you count how many 3-digit numbers that we can form from the digits 5, 7, and 4, we have only 6 3-digit numbers. Now let's proceed to our second method of solving this problem. So we will answer the first question when repetition is allowed. So here I will make 3 boxes. One for the hundreds place, and the second box is for the tens place, and the last box is for the ones place. And looking for the 3 numbers which we can choose from, we can place 5 in the hundreds place, or 7 in the hundreds place, or maybe 4 in the hundreds place. So we can choose any of the 3 numbers in the hundreds place. But in the tens place, I can choose also any of the 3 digits because repetition is allowed. For example, if I have placed 5 in the hundreds place, I can still place 5 in the tens place because repetition is allowed. So any of the 3 digits can be placed in the tens place. And also in the ones place, I can choose any of the 3 digits. So using the fundamental principle of counting, I can multiply these numbers and the product is 27. So therefore, we can say that there are 27 three-digit numbers that we can form from these 3 numbers when repetition is allowed. And you can see that I have the same answer with the first method, which is the tree diagram. So either you can list down all possible 3-digit numbers you can form, or you can use the fundamental principle of counting. However, in the listing method, it's a little bit tedious because you will be listing all possible 3-digit numbers. Now, sometimes or most of the time, listing is not possible, especially if the list of all possible occurrences is so large. So therefore, we can use our box method here by placing all possible occurrences in each box. Now, let's proceed to our second question. When repetition is not allowed. So here, I will be constructing 3 boxes. One for the hundreds place, the second one is for the tens place, and of course, the last box for the ones place because we are constructing a 3-digit numbers. Now, in the hundreds place, I can choose any of the 3 numbers to be placed in the hundreds place. I can place 5 or 7 or 4 in the hundreds place. So I have 3 choices. But in the tens place, once one of the 3-digit numbers is being placed in the hundreds place, I cannot place anymore that number in the tens place because repetition is not allowed. For example, if I have placed 5 in the hundreds place, then I cannot use 5 in the tens place. So I am left with 2 choices at this time for the tens place. And if I have placed any of the 2 numbers from 5, 7, or 4 for the 2 places, for the hundreds place and the tens place, then I cannot use those numbers in the ones place. So I am left with 1 choice only. So multiplying these numbers, we have 3 times 2 times 1. The product is 6. So therefore, there are 6 3-digit numbers we can form from 5, 7, or 4. And you notice that our answer here is the same answer we have when we use the tree diagram. Now let's proceed to our second example here. A car license plate number starts with 3 letters from the English alphabet and is followed by 3 numbers. So the question, how many car plates can be produced by the Land Transportation Office when repetition of letter and number is not allowed here? Letter B, when repetition of letters only is allowed. Letter C, when repetition of numbers only is allowed. Letter D, when repetition of letters and numbers are not allowed. So let us first solve our first question, when repetition of letters and numbers are not allowed. So here I will be drawing the 3 boxes for the position of the first 3 letters, and then another 3 boxes for the position of the 3 digits, because the license plate number starts with 3 letters from our English alphabet and then followed by the 3 numbers. Now, when repetition of letters is allowed, I can place 26 in the first position of the first letter, since there are 26 letters in the English alphabet from A to Z. And then 26 also for the second position, because if you use, for example, letter A in the first position, I can also place A in the second position because repetition is allowed here. And also in the third position, I can use the same letter in the third position. And in the number, I can choose from 0 to 9. So I have 10 choices for that position of the first number. Also, in the second position of the three numbers, I can choose from 0 to 9. So I have 10 choices. And so with the last position. Now, multiplying these numbers, I get a product of 17,576,000 plate numbers. So, when repetition of letters and numbers are allowed, I can produce 17,576,000 plate numbers here when repetition of letters and numbers are allowed. Letter B, if repetition of letters only is allowed. So, in the first position of the letter, I can choose any of the 26 letters of our English alphabet. And also in the second position, I can choose any letter because repetition of letters is allowed here. And for the first position of the three numbers, I can choose from 0 to 9 here. But in the second number, I am left with 9 choices here because if one number from 0 to 9 is being placed in the first position of the three numbers, then I cannot use that number in the second position. So I am left with 9 choices here. And for the third number, if 2 out of the 10 numbers from 0 to 9 are being placed in the first two positions, I cannot use those numbers in the third position. So I am left with 8 choices here. So multiplying these numbers, I will get 12,654,720 plate numbers when repetition of letters only is allowed. Now letter C, when repetition of numbers only is allowed. So for the first letter, I can choose any of the 26 letters of our English alphabet. But in the second place, I am left with 25 choices because one of the letter in the 26 letters is being placed already in the first position. So I cannot use that letter in the second position. And also in the third position, I am left with 24 choices because 2 of the 26 letters of our English alphabet are being used already for the two positions. So we have there 26 choices for the first letter and then 25 choices in the second letter and then 24 choices in the last letter. And for the first number, I can choose any of the 10 numbers from 0 to 9. And also 10 choices for the second position because repetition of number is allowed here. Then, therefore, I can use also any of the 10 numbers for the third position. So therefore, multiplying these numbers, I will get a product of 15,600,000 plate numbers here. And then, for the last question, when repetition of letters and numbers are not allowed, I will again draw these boxes here. So the first 3 boxes for the first 3 letters, I can choose any of the 26 alphabet for the first letter there. And 25 for the second position because one of the 26 letters is being used in the first position. And in the third position, I am left with 24 choices. But for the first number, I can use any of the 10 numbers from 0 to 9 in the first position. But in the second position of the numbers, I am left with 9 choices here. And 8 also in the third box, because if 2 of the 10 numbers are being used in the first 2 positions, I am left with 8 choices now. So multiplying these numbers, I will get a product of 11,232,000 plate numbers. So these are the answers for the 4 questions in this example using the fundamental principle of counting here. Now let's proceed to our third example. How many 3-digit odd numbers can be formed from the digits 1, 2, 3, and 4 if no digits are to be repeated? So solving this third example, I will be constructing 3 boxes here because this is a 3-digit number. The first box is for the ones place, and the second box is for the tens place, and then the third box for the hundreds place. And because it is being specified in the problem that this is an odd number, I should start in the ones place so as to restrict this 3-digit number as an odd number. Now looking at these numbers 1, 2, 3, and 4, only the numbers 1 and 3 can be placed in the ones place so that this 3-digit number can be an odd number. And why is that? Because an odd number is a number that ends with an odd number. So I have only 2 choices in the ones place. I can place there 1 or I can place there 3. So it's a 3-digit number that ends with 1 or 3. But in the tens place, I am left with 3 choices. Why? Because one of the digit in the 4 numbers there is being used in the ones place. So for example, if 1 is being placed in the ones place, then I cannot use 1 in the ones place. I am left with 2, 3, or 4 as the choices for the tens place. But in the hundreds place, I am also left with 2 numbers because 2 of the 4 numbers are being used in the tens and the ones place. And then multiplying these numbers, I will get a product of 12. So there will be 12 3-digit odd numbers can be formed by these 4 numbers. So here we were able to know the 3-digit odd numbers even without listing them because we are using here the fundamental principle of counting. Now let's proceed to our example number 4. In how many ways can 7 persons be seated in 9 chairs? So solving this problem, I will create 7 boxes. And these 7 boxes represents the 7 persons. Now let's consider the first person here. If this person is the first person to choose the 9 vacant chairs, so this first person has 9 choices. He or she can sit any of the 9 chairs. Maybe he can choose the first chair, or the second chair, or the third chair, or the fourth chair, up to the last chair. So the second person can choose only 8 because the first person has chosen already his chair. And the third person is left with 7 choices now because 2 of the chairs were being used by the 2 persons. So he is left with 7 choices. The fourth person, 6 chairs only. And so with the 5th person, the 6th person, and the 7th person there. Because the 7th person is left with 3 chairs. Since 6 of them were able to sit the 6 chairs. So 6 out of the 9 chairs are being used already for the 6 people. So the last person to choose is left with 3 chairs. And then multiplying these numbers, we get 181,440 ways. And in this case, we were able to know the number of possible ways without listing them because we are using here the fundamental principle of counting. Now let's proceed to this example here. A church has one front door here, 4 doors on the left, 4 doors on the right, and 2 back doors here. So the question is, how many ways can Rod enter and leave the church if he enters and leaves through any door? So let's try first answering this first question. If he enters and leaves through any door. So here, I will be constructing 2 boxes. One box for the number of possible entrance, and the second box is for the number of possible exit here. So if he enters the church, he can choose any of the 11 doors. He may choose to enter in the front door or any of the left side doors or the right side doors or any of the 2 back doors. And then, leaving the church, he can choose any of the 11 doors because he can leave the church using any door. So 11 times 11 here. And then multiplying these numbers, we've got 121 ways when Rod enters and leaves the church using any door. But what if he enters and leaves through different doors? This means that the door he used for entrance cannot be used for his exit. So here, I'll be drawing 2 boxes. And in the first box is the number of ways for his entrance door. And he can choose that from any of the 11 doors. But for his exit, the door that he used for entering the church cannot be used for his exit door. So he is left with 10 doors only. So multiplying these numbers, we get 110 ways if he enters and leaves the church through different doors. Now let's proceed to the third question. If he enters and leaves by the same door. Now, for his entrance, he can choose any of the 11 doors. But leaving the church, he is left with one choice because he must have to use his entrance door as his exit door here. So, multiplying these numbers, he has only 11 ways of doing that. Now, let's proceed to the fourth question here. How many ways he can enter through the front door and leaves the church through any door other than the front door? So, for his entrance, he can choose only one since the church has only one front door. But for his exit door, he can choose any of the 10 because he cannot use the front door as his exit door. Now, multiplying these numbers, we get a product of 10. So there are 10 ways of entering the church using a front door and leaves the church through any door other than the front door. But in the fifth question, if he enters through the front door and leaves through a back door, then he can choose only one door for his entrance door because again the church has only one front door. But he leaves the church through any of the back doors. So he is left for 2 choices now for his exit. And then multiplying these numbers, we get 2 ways. But what if he enters through any side door and leaves through any door on the same side? So for his entrance door, he can choose any of the 8 doors. 4 doors on the left or 4 doors on the right. So therefore, he can choose any of the 8 doors for his entrance door. And for his exit door, he is left only with 3 doors. Because if he entered in the left door, he cannot use that door for his exit. So therefore, he must have to choose any of the three doors that is not used as his entrance door. So therefore he is left with three choices here. And then multiplying these numbers, we get a product of 24. Now, what if he enters through a side door and leaves through a door on the opposite side? So, for his entrance door, he can choose any of the 8 doors. Any door from the left or any door from the right. But for his exit door, he must have to choose any door on the opposite side. So, if he enters through a left door, he must have to exit using a door on the right. So that's why he is left with 4 choices here. So multiplying these numbers, we get a product of 32 here. But what if he enters through any side door and leaves through the back door? Then therefore, for his entrance door, he can choose any of the 8. But leaving the church, he can choose only 2 doors because there are 2 back doors in this church. So now let's proceed to the 9th question here. What if he enters through a back door and leaves through another back door? So for his entrance, he can choose any of the 2 back doors. But leaving the church, he is left with only 1 door because he cannot use that back door that is being used for his entrance door. So you have now 2 ways of doing that. But if he enters through a door on the left side of the church and leaves through the front door, he can choose any of the 4 doors on the left and then leaving the church with only 1 door because the church has only 1 front door. Hence, there are only 4 ways you can do that. Now let's proceed to our most commonly used notation in probability, which is the factorial notation. The product of the positive integers from 1 to n inclusive occurs very often in mathematics, and hence it is denoted by this symbol here, which is read as n factorial. So the definition of this n factorial is the product of the integers starting from 1 times 2 times 3 up to n. So therefore, if you multiply the positive integers from 1 to n, the integer before n is n minus 1 here. And then before n minus 1, we have n minus 2. So that is why n factorial is a product of the numbers from 1, 2, 3, up to n minus 2 times n minus 1, and then n. Because you see, the numbers are increasing from 1 to n. So let us have examples here that would illustrate that factorial notation. Now, what is 2 factorial? 2 factorial is the product of the numbers 1 and 2 here. So 2 factorial is 2. But what is 3 factorial? 3 factorial is the product from 1 to 3. So multiplying 1 times 2 times 3, we have a product of 6. Then therefore, 3 factorial is 6. What is 4 factorial here? 4 factorial is again a product from 1 to 4. So multiplying these numbers, 1 times 2 times 3 times 4, we have a product of 24. So also for the 5 factorial, 5 factorial is a product of the numbers from 1 to 5. So multiplying these numbers, 1 times 2, which is 2, and then times 3, which is 6, and then times 4, which is 24, and then multiplying it by 5, we have a product of 120. Then therefore, 5 factorial is 120. What is 7 factorial? 7 factorial is a product of the integers from 1 to 7. And multiplying these numbers, we get a product of 5040. Thus, 7 factorial is 5040. Now, what is 7 factorial divided by 4 factorial? 7 factorial, we know that's a product from 1 to 7. And 4 factorial is also a product from 1 to 4. So, canceling these factors 1, 2, 3, and 4 from the numerator and from the denominator, then we are left for the product of the numbers 5, 6, and 7 here. So therefore, 7 factorial divided by 4 factorial is 210. Now, what is 8 factorial divided by 6 factorial? 8 factorial is a product from 1 to 8, and 6 factorial also is a product from the integers of 1 to 6. But 8 factorial is equal to 6 factorial times 7 times 8, and the denominator, which is the product of the integers from 1 to 6, can be written also as 6 factorial. So therefore, we can cancel the 6 factorial from the numerator here. So we are left with the product of 7 and 8. Thus, 8 factorial divided by 6 factorial is 56 here. Now, at this time, we will present to you two ways to express n factorial here. And since multiplication is commutative, then we can write also our n factorial in the reverse order. So instead of multiplying the numbers from 1 to n, I will express n factorial as a product starting from n. So n times the next integer smaller than n, which is n minus 1, and then n minus 2, and then n minus 3 up to 1. But this product from n minus 1 up to n minus 3 factorial can be expressed as n minus 1 factorial, because this is a product of integers from n minus 1 up to the last integer, which is 1. So n factorial is equal to n times n minus 1 factorial. So therefore, we can show to you what is 0 factorial. So since 1 factorial is 1, then we can show that 0 factorial is also 1 by using the definition of factorial, that n factorial is the product from 1 to n. But this product can be written in the reverse order. So I can start with n, and then n minus 1, n minus 2, and so on and so forth until 1. But this n minus 1 up to 1 can be written as n minus 1 factorial. So when n is equal to 1, we can substitute that 1 for our n. So 1 factorial is equal to 1 times 1 minus 1 quantity factorial. But we know that 1 minus 1 is equal to 0. So here, 1 factorial is equal to 1 times the 0 factorial. Now, suppose here we don't know what is 0 factorial. But 0 factorial is multiplied by 1. Then therefore, it is just equal to 0 factorial, because 1 is the multiplicative identity here. Hence, 0 factorial is equal to 1. And that's the proof that 0 factorial is equal to 1 by using the definition of factorial. Now, let us simplify this expression here. What is n plus 1 quantity factorial divided by n minus 1 quantity factorial? N plus 1 factorial can be written as 1 times 2 times 3 up to n, and then n plus 1 here. And in the denominator, we start also from 1. So 1 times 2 times 3 up to n minus 1. So canceling the common factors from the numerator and the denominator, we are left with n times n plus 1. So therefore, the answer is n times n plus 1. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.